I'm going to start with quite another Maori greeting. Kia tere e ho, kia tere. Get on with it. We've been hearing this morning about we're going to do this, we're going to do that. Now we're hearing what actually gets done. These are people that are actually doing the mahi and getting the results. Just a wee story to start this off, because I'm going to hand over to the people that are really doing it very shortly. I want to go back to the 1970s and 80s when government science dropped the ball. They let loose into the environment all of their native forest scientists and let them go, and did very little work from then on. Then my very good friend Rob McGowan said, we've got to do something about this. There's a great big hole we've got to fill. And so for the last 23 years, we in Tarnish Tree Trust have been filling that hole and doing the mahi. And we're going to talk today about one hole that really needs to be filled, and that is the amount of carbon sequestration that native trees really do. Because the only number that the government will give us is that which was done for scrub. That's the lookup table. And I'm going to give you some numbers, 6.5. We're talking about tons of carbon dioxide sequestered per hectare per year. That's the only number that we have officially in the government tables. We're going to move on and talk about, first of all, we acknowledge that native trees do sequester carbon. And we think they do it quite well. They've been doing it for quite a while. And we're going to talk about some numbers. But before that, to recognise yet again the way in which we have removed forests from this country. And while we decry what's happening in the Pacific with oil palm and in the Brazil with the forests there, we've done it all already, big time. We've done it all already. So on the right-hand side, you can see what we've got left. There should have been a table there. There's not. But this is the history of the logging. I'm sure you've all read A.H. Reid's story of the Kauri, and the depressing tales there of the 90% of the Kauri resource which was just lost and burnt. And here's a burn here. We missed a table, but I'm just going to give you some numbers. They were on the table, and somehow we've missed it. I'm going to give you three numbers. 6.5 is the carbon sequestration rate that is given in the lookup tables for native forests. It's actually a native scrub, Manuka carnica scrub on the east coast. It's not native forest. And then if we look at the world average forest carbon dioxide sequestration, we're getting numbers like 6 to 8. Our problem in this country, we've got this amazing tree radiata which can go to 40. But in between we've got other numbers, so I'll give you another number, around 15. And I'm going to introduce you now to David Bergin, who has done this amazing job in plots and getting the database for the growth rate of trees that are managed, native trees that are managed. David, over to you.
Thanks, Warwick. We've seen this climate change slide before with various other speakers this morning, so I won't focus on it too long. But I just think what the Climate Change Commission have been doing with their recommendations to government is just fantastic, and there's some really good pointers in there. If you go down to bullet number 3, for instance, you only have to talk and for not very long to find out just how devastating our pests are in our forests, both pre-1990, and for anyone who's done any planting or wanting to encourage regeneration, one of our biggest factors that are stopping successful restoration of native forests is pests. So I absolutely fully endorse that we need to get on top of our pest browsing animals and our bird predators as well. The number fourth bullet point, we know that we will want to plant more trees, and we've got this figure of 300,000 hectares of new native forest. A lot of it's going to be like that, marginal land, 1 million hectares of marginal land, thereabouts. Most of it's going to be skeletal soils on really rough ground, 45 degrees, that sort of thing. You're not even going to get many contractors going into that sort of country to plant natives. And especially if you're looking at planting at cost of, 6,000 to 10,000 up to what I saw on a slide this morning, $180,000 per hectare. If you think you're going to be planting that sort of country in the magnitudes of 300,000 hectares, you've got to be joking. So what can we do to help nature do the job for us? And again, it comes back to sorting out what are those factors that are the biggest issue with our return of our native forests. Our forests are remarkably resilient, but there are some major factors that need to be addressed, such as the pest animal control, such as bringing back the seed sources and all that sort of stuff. So it's all about the innovation around that, and it's not high-tech innovation. It's just common sense. Get out there and do the hard yards on the ground. And the reason why I'm just sort of trying to stress the regeneration versus planting is that I think there's still scope for both. All right, I've spent 40 years on planting, and I still think planting, raising seedlings, all that sort of stuff is absolutely important and is going to be a part of large-scale regeneration of our 1 million hectares of marginal land, and there's no way we can get away with it. So what I'm trying to do is set the scene for what Mark is going to be showing you in terms of the carbon that will be coming from both regeneration as well as for planted stands. So we've got basically most of our work is focused on planted stands. We've got the largest plantation database in the country. This is the result of 2 surveys. The first one was done by FRI in 1986, of which I was involved in. I'm that old. And then Tane's Tree Trust repeated that in 2010. And you can sort of see there, we took part of that plantation database, and you will see in the rest of the talk the growth models, the carbon models that we generated from that. The map there just shows you all the plots that we've put in throughout the country that basically represent the data that's underpinning the carbon and growth models. So for this study, we had 124 plots. We tried to avoid plots that had large edge effects, all that sort of stuff, all the shelter belts out of it, so it's only internal trees. And you can sort of see that we had 3,700 trees and 1,600 shrubs as part of our database, so quite a small database. Mean age was 38 years, and the range from 9 to 110 years. And the stocking overall for the trees was about 1,400 stems per hectare. But there were 75 different species in those plantations. Many of them were just single species plantations, but a lot of them were mixed species plantations, but nevertheless there was a hell of a lot of species within them. And right now we are in the midst of a new survey, which we're going to expand the database quite substantially and start picking up on another point that the Climate Change Commission is why aren't we measuring the carbon in a lot of small blocks, riparian areas, shelter belts, all that sort of stuff to do with farms, which we totally agree with. So that will become part of our new survey. And on top of that, we've also got some work from Northland and East Coast to do with shrubland and totara in Northland, and then the Manuka Kānaka work that we did after Bowler on the East Coast. And just a couple of, this is my last slide, just a couple of slides there just showing you on the left-hand side there, 100-year-old planted stand of totara and puripuri in the centre of Northland. That's at a succession of dairy farmers. When Michael and I turn up there every sort of 5 to 10 years and get a new farmer, he's absolutely convinced it's a natural stand, but it's actually planted. You can actually see rows in that stand, but that's over 100 years old now. Quite high stockings and very high volumes. If it had been thinned out 50 years ago, some of those trees would be twice the size and diameter. And on the right-hand side, there's Dame Anne's property there at Waikiraroo, just showing an example of after 20 years of managed, assisted natural regeneration. All the stuff on the left-hand side there is mostly karna coming back on those steep slopes. And we've just sort of started a project there, putting in planted seed islands along the base of those slopes there as seed islands, if you like, to get other species up to the steep slopes, to let the natural drones that we have around us, which are the birds and the wind, do the hard job for us. Okay, I hope that sort of leads into your some of your graphs.
Okay, thank you, David and Warwick. So I'll take over now, and so the database that David has just described, I'll go through some of the numbers that come out when we work out carbon values from that data. But just before we do that, I'll just give you a sort of more of a global perspective of what sort of carbon sequestration rates do we expect in forest globally. And so the IPCC has provided these numbers. They're the best estimates by international experts on growth rates in terms of carbon in different forest types around the world. If you look at this column here, the first six numbers are naturally regenerating forests globally, and you see they range hugely. Like wet tropical or subtropical forests can average around 12 to 13 tonnes of CO2 per hectare per year, down to very low rates in the in the Arctic, where maybe less than 1 tonne per hectare per year. But for New Zealand, from New Zealand's perspective, I guess the relevant numbers are these two here. This is the temperate zone, which is where we belong, and average rates tend to be globally around 7 to 9 tonnes of CO2 per hectare per year. So just bear that in mind. And also IPCC provide numbers for fast-growing pine and eucalypt forests, and obviously these are much higher than the naturally regenerating forest. Tropical wet forest, highest for pines, up to 35 tonnes, and eucalypts similarly around 30 tonnes. So those are the sort of numbers that are, we find globally, internationally. So let's now move on to the sort of analysis we can do with our data, our growth data. We have graphs that look like this. So on the vertical axis, we've got the carbon sequestration, and on the horizontal axis is the age of the forest. So all these forests, they're planted forests, so they start off with small seedlings in the ground, or they're regenerating forests, which are establishing from usually from grassland. So they start off at a very low level, virtually zero, and the first maybe decade or two, while the trees are establishing, growth is fairly slow. But once the crowns occupy the site and can maximise the amount of sunlight coming in and the crowns close, then the growth rate rapidly increases and reaches a maximum. And eventually a forest, any forest, the trees start growing, trees start dying, and you start to lose carbon through mortality, and eventually, although even an old tree continues to grow and sequester carbon, it's balanced by the loss of growth in trees that die. So eventually you reach an equilibrium, and we call this level the carbon carrying capacity of the forest. So in this particular example, it's around 2,000 tonnes. So, but it's taken maybe 200 years to reach there. But in terms of the metrics that we're talking about today, there's two that are relevant. One is the MAI, which is the mean annual increment. That is the carbon stock at a certain age, say at age 50, divided by that age. So in this example, we have 500 tonnes at age 50. So we divide that 500 by 50 and it comes out to 10. So the MAI of that forest is 10 tonnes per hectare per year. It's the average growth shown by this red line up to that age. But because that includes those early years when the growth was very slow, it's actually a slower rate than the annual rate we're getting at that point once we reach 50 years, and that's what's indicated by the CAI, or current annual increment, which is the slope of the line at this point. So we're mainly going to be talking about MAI, so mean annual increment, how much carbon we've got at a certain age divided by that age. And so how do we actually measure carbon in a forest? So there's a kind of a standard method that is used. If we want to establish how much carbon is in a forest, we put in a plot, a growth plot. Usually it might be something like a 20-metre radius plot. And we measure all the trees in that plot. So we measure their diameters and heights. And we have equations that we can use to convert those measures of diameter and height into volume. And then we multiply that up by the density of the wood in those trees, which will vary with the species. And that gives us an estimate of the biomass, like the dry matter in that stem. We add something to account for the other bits of the tree, like the branches, foliage, and the roots. And that gives us basically the weight of that, the dry weight of that tree, how much material is in it. And we know that half of that weight is actually carbon, which has been sequestered from the atmosphere. So that's basically how we do it. So we add up all those trees in that plot, and if we divide it by the area of the plot, it gives us the carbon per hectare for that plot. All these methods were developed by Scion a few years ago, and they've been well validated and pretty much accepted. So we can use them in both planted forests and in regenerating forests. So now I'm going to present a series of graphs which show the results from our planted stands. So again, we are showing carbon on the vertical axis and the age of the stand on the horizontal axis. The green points, each of those is a measurement plot, so it might consist of maybe 30 trees or something like that, a mean of, so it's the carbon in that plot converted into a per hectare value. And the line is just the line is just a fitted curve through those points. So these points represent planted native shrubs. So they're things like manuka, mainly kanuka, and many other broadleaf shrubs that are widely used for planting riparian areas and so on. And our data is a bit limited. It's limited in terms of age. We only go up to about age 20, but you can see fairly rapid sequestration rates up to around 17 tonnes per hectare per year at age 20. But the line is probably going to flatten out after that, because the upper limit, the carbon carrying capacity of a shrubland stand is not particularly high. But still, it's a good rate of sequestration for the first 20 to 30 years. If we now look at a tall forest species, which is, this one is totara, we see a slightly different pattern to the shrubs. If I just go back to the shrubs, you can see the shrub planting has produced higher rates, mainly because they are planted at a higher density. The totara takes longer to get going, but once it establishes and the crowns are fully developed, it chugs along quite well. In fact, its MAI at age 50 years is only around 11 tonnes per hectare per year, but its CAI is up to about 19 tonnes at that age. That's the slope of the line at this particular point. So that's totara. We look at kauri. It's similar to totara, but a little bit faster growing. Its MAI is around 16 tonnes at age 50. This is all other native conifers, so things like remu and kahikatea mainly. And you can see there's a wide range of, a wide spread of points. But the mean value, the mean curve is quite similar, somewhere between totara and kauri. And if we look, this slide is native broadleaves, which are mainly beech and some rereba and puriri. They've all been combined together. Again, the results are quite similar to the native conifers. Now, so those are all planted stands. Now, we've just got two examples that in our data of naturally regenerating forest. And this has not been purposely naturally regenerated. This is just areas of farmland that have been allowed to revert to native forest for various reasons. This is a survey done on the east coast of the North Island after Cyclone Bowler, which was done principally with the intention of looking at the effect of native vegetation on slipping and that sort of thing. But we've been able to convert that into carbon estimates. And what we find is that on this these native regenerating shrublands, it's mainly almost entirely manuka and kanuka. The growth rate initially is quite high, maybe around 10 tonnes per hectare per year. But it flattens off quite early because those kinds of forests don't have a very high carbon carrying capacity. So after around 30 years, it pretty much flatlines. Because we don't have tall trees, it's mainly manuka kanuka. And really, there's an absence of other species in that forest. In contrast, we've got this regenerating forest from Northland, which is dominated by totara. So there's also contains kanuka and other species, but particularly with time, the totara has become dominant. And the thing, if you compare those two examples of regenerating forests in the North Island, so that's kanuka manuka on the east coast, this is totara in Northland, you can see a huge difference. The totara forest is just continuing to increase. And you can see we've got some plots there that are aged over 100 years, 130 years. They've already reached 1,000 tonnes. So average sequestration rate is around 8 tonnes per hectare per year in that data set. We also have some permanent measurement plots in some of those stands, and over an 8-year period they've been averaging around 10 tonnes per hectare per year. So this is putting all those curves together on one graph, which is a little bit confusing perhaps, but what we've got is a bunch, these lines here are the planted natives, these are the planted shrubs. So you can see the planted shrubs produce quite a rapid sequestration early, mainly because they tend to be planted at higher density. But then they'll flatten out probably by age 30 years or so. The native tree species are a bit slow to begin with, but then they start sequestering quite well. So this red line is totara, this blue line is the broadleafed natives, this green line is kauri. So the rates of all those different species are quite similar. The regenerating totara is down here, so somewhat lower than planted totara, probably for various reasons, but mainly because the sites tend to be poorer. The east coast shrubland, regenerating shrubland is here, so as you see it's quite good to begin with, and then it flattens off. And just for context, we put in here the IPCC global values for regenerating forest on temperate climatic zone, and you can see it's pretty much in line with New Zealand regenerating totara. And we've also added radiata pine, which again, as the IPCC points out, is giving you very high levels of sequestration. So that's kind of the overall picture. This table is just giving some of these numbers, which obviously I won't go through all of it, but what we see, for example, is planted kauri has an MAI of 16, its CAI is by age 50 is around 25, actually around about the same as radiata pine at that age. But of course radiata pine has sequestered very rapidly over the earlier part of its, over the first few decades. So its carbon stock is very high. So just to summarise then, I think what our data shows is that sequestration rates of regenerating native forest in North Island sites anyhow, and certainly you won't necessarily get those rates in colder or drier sites, but the two examples we've got from the North Island, they're pretty much in line with the global averages for temperate forests. Regenerating totara is around 8 tonnes per hectare per year, and it will go on at least to 130 years, which is our oldest plot, but I'm sure it will go much, much longer than that. The problem with the shrubland on the east coast was that it's basically very few species, just manuka and kanuka, and they don't have a very high carbon carrying capacity. So although the sequestration rate is fast to begin with, it tends to flatten out. Planted natives generally can do quite a bit faster growth than these regenerating natives, around about 11 to 16 tonnes over 50 years. And also the other point we make is in line with global results, global averages. Radiata pine or some other exotics obviously can sequester very fast, up to 40 tonnes in fact. There's just a few references, and
we've just launched our toolkit yesterday on their website, and that includes 4 calculators, one on economics, one on planting and budgeting, and another on growth and yield, and it also contains the carbon calculator that Warwick talked about as well. So go on to the Tāne Street Trust website and you'll see it on the front page, and give it a go and give us some feedback on it.